Let's look at a couple examples of finding the row space or describing the row space of a matrix and finding its rank. So maybe I should add a question about rank to this. So let's also find rank of this matrix. So we know to do this, we can find a basis for the row space of this matrix just by taking the non-zero rows after we've done row reduction, right? So let's do row reduction. And I was thinking ahead, and I have the result of row reduction right down here. So there's the reduced row echelon form for this matrix. For a basis for the row space, we just need to write down the rows of this matrix. So basis for the row space of our matrix A, this is A. We can get a basis just by taking these rows. So 1, 0, 0, minus 2, minus 2. I'm writing them as columns. It's not really important whether we write them as columns or not. If you want to keep them as rows, I guess you can do a transpose, right? But for the moment, it's not important whether we think about them as rows or columns. 0, 1, 0, 0, 1, and 0, 0, 1, 2, minus 2. All right, and sure enough, these are linearly independent, as we knew they would have to be. Non-zero rows of a reduced row echelon form are always linearly independent, as we know. So the row space is, so this is a basis for the row space. So row space of A is the span of these three vectors. And this also shows us that it tells us what the rank of A is. Remember, the rank of a matrix is the dimension of the row space of the matrix. And we just saw that, right, this is a basis for the row space. So we have a row space with 3 vectors in it. That means that the dimension is 3. Right? The dimension is the size of a basis, and every basis has the same number of vectors. We proved that. So the rank of this is 3. All right, let's look at another example. Let's find a basis for the span of these vectors. Now, this doesn't obviously have anything to do with row spaces, but to find a basis for a span, well, if these were rows in a matrix, we could find a basis for the span of the rows by doing row reduction and then taking the non-zero rows. Well, we can make these be the rows of a matrix. Just sort of turn them on their sides. That's called taking a transpose, and then stuff them into a matrix. So, right, this first column vector will turn into our first row, and then second column becomes our second row, so minus 1, 3, minus 2, minus 2, minus 2, 6, minus 5, minus 6. Okay, so the row space of this matrix is, so let me call this A. So row space of A. We've arranged things so that the row space of A is the span of V1, V2, and V3. Right? So to find a basis for this, just do row reduction. And I have the result down here. So now that we have this row reduction, we can write down the basis. So basis for the row space of A is just the non-zero rows of this. So 1, minus 3, 0, minus 2, and 0, 0, 1, 2. Okay. And of course, we set things up so that the row space of A is the span of V1, V2, and V3. So here we have a basis for the span of those vectors. by taking this sort of detour through a row space. Even though the question didn't have anything to do with row spaces at the beginning, we can sort of rephrase it in terms of rows by turning these vectors on their sides and then putting them into a matrix.